In this video, we're going to look at the notes for 1.2, conservation laws. A conservation law is a mathematical formulation of the fact that the rate at which a quantity changes in a given domain must equal the rate at which the quantity flows across the boundary, plus the rate at which the quantity is created within the domain. So let's suppose that we have a tube, as you can see here. We're imagining that it has cross-sectional area that is some constant a. So for any x value on our x-axis, we'll have the same cross-sectional area. Let u equal some function of x and t, where x is this spatial dimension, and we think of t as time. So let u be the density of some quantity in the tube. What that quantity is arbitrary at this time. So let u at xt be the density of some quantity in the tube at position x at time t. So we assume the value of u at xt is constant within the cross-section. So that is to say that we're imagining that the value or the density is the same anywhere within this cross-section of the tube. So the amount of the quantity in some lamina, that just means some really thin little region. So the amount of the quantity in a lamina of width dx, so we're imagining that it has this infinitesimal width, is going to be given by u at xt, the density, times the cross-sectional area times this infinitesimal width dx. So that's the amount of quantity in just this little cross-section here. All right, well, now let's let phi be the flux at position t and time t, position x and time t. The flux at xt measures the amount of the quantity crossing the section at x. So it's measuring the amount of the quantity passing through your cross-section at position x and time t per unit area. So what that means is that if you look at a times phi at xt, that's going to give you the actual amount passing through the cross-section at x at time t. So as a convention, we say that the flux is positive if it's flowing to the right, and the flux is negative if the flow is to the left. So in this image here, we're imagining that the flux is positive, it's flowing to the right. So let f at xt be the rate at which the quantity is created or destroyed within the cross-section at x and time t. So we fixed an x and we fixed a certain time, so we're looking at a cross-section here. Now it might be that the quantity is being created or destroyed, and the rate at which that quantity is being created or destroyed within that cross-section is given by this value, f at xt. We have some terminology for this. If f is positive, so something's being created, then we call f a source. And if it's disappearing, if it's being destroyed, then f is negative and we call it a sink. If we're not making any particular assumption about whether it's a source or a sink, we usually just call it a source, with the understanding that if it's negative, it's actually a sink, but it's just easier to say one or the other sometimes. The units of the source or the sink are amount per unit volume per unit time. So if you look at f at xt times a times dx, that's going to give you the amount created in the cross-section at x per unit time at any given time t. So a conservation law is going to be a relation between these three quantities, u, phi, and f. So it's a relation between the state, which is u, the flux, which is phi, and the source or sink, which is f. So let's look at our picture again. So we have this tube, and remember u is giving us the density of something within that tube. And so the rate of change over this entire interval from a to b, from the left endpoint to the right endpoint, the rate of change is going to be equal to the rate at which it flows in at the left endpoint, here, minus the rate that it's flowing out over here at b, plus the rate it's created within the tube. So it's flowing in on the left end, it's flowing out on the right end, and it may be created or destroyed inside. So the conservation law is telling us that the rate of change over this interval from A to B is given by the rate it flows in at A minus the rate it flows out at B plus the rate it's created or destroyed inside of the tube. Now these are things that we can write down in terms of our state, our flux, and our source term. And we've done that here. So let's look at the left here. We have the integral from A to B u xt times A dx. This is the total amount in the tube from A to B at a specific time. So the value of this quantity depends on time. So this is a function of time. Remember that u xt, that's the density. So then you multiply it by A and dx, and that's going to give us the quantity in that one little slice, or maybe this slice right here, because that's the one that has width dx. So if you add all of those together, so to speak, if you integrate it, that's going to give you the total amount in the tube. Now what we're interested in is the rate of change of the quantity in the tube over time. So how do we compute the rate of change over time? We compute the derivative, d by dt. So that's the thing on the left. What about on the right? This term, a times phi at at, that's the rate at which it's flowing in at time a. And this term right here, that's the rate at which it's flowing out at time b. That's why there's a minus sign there, because we're taking out how much is flowing through at b at that particular time. And what about this term here? Well, this is f is our source term. It's telling us how much is being created. So remember, f at xt times a times dx, this term right here, that was the amount that was being created in the cross-section at x per unit time. So if we integrate, that's going to add together all of the contributions throughout the tube. So that's going to give us the rate at which it's being created or destroyed. So if f is a source, if f is positive, then the substance is being created. And if f is a sink or negative, then it's being destroyed. So this integral may be positive or negative. It might be positive for some values of x and negative for other values of x. So what we're looking at here is the total over the entire tube from A to B. We're adding them all together to get the total amount. But this is a rate. This is the rate at which it's being created or destroyed in the whole tube here. So if we add all of this together on the right, we're going to get the quantity on the left. That's our conservation law. Now we remember that a is a constant, so that means we can just divide by a and get rid of all of those a's. And that's what gives us this equation right there. So let's take a look at these terms. So on the left, we're computing the derivative with respect to t of some function of t. It is an integral, but notice that we're integrating with respect to x. So that means you can take the derivative inside. This is what's usually known as Leibniz's rule for integrals. So that means that the derivative of this integral is the integral of this derivative, the integral from a to b of the partial derivative of u with respect to t. Now, on the outside here, this is not a partial derivative because you're integrating with respect to x. So once you've computed that, there's no x's left. It's just a function of t. So when you're differentiating it outside, there's no partial derivative there. But when you take it on the inside, then it is a partial derivative because there's still an x there. But the idea behind the partial derivative is you treat x as a constant. Okay, so on the left we have this integral. The integral from a to b of u sub t x at t dx. So that's the left term. What about on the right? Well, notice that this difference here, u at at minus, or not u, phi at at minus phi at bt, by the fundamental theorem of calculus, This is the opposite of the definite integral from a to b of phi sub x. So again, we're integrating with respect to x here. So the fundamental theorem of calculus tells us that this integral is, well, we've got a minus sign here. So this is going to be equal to minus phi at b comma t minus phi at a comma t. And now you can see the reason for that minus sign out here, because in our conservation law, we have phi at a comma t minus phi at b comma t. And the fundamental theorem of calculus gave us the wrong direction, so to speak, so you need that minus sign in front. So what that means is we can write this difference as an integral with respect to x, and that's what we've done here. So that's what we have there. We haven't done anything with this integral of the source term, but it was already an integral with respect to x. On the left, we have an integral with respect to x as well. So what we're going to do is we're going to take these terms on the right and we're going to move them over to the left. And then you get one integral, which is equal to 0. So the integral that has an integrand, which is u sub t plus phi sub x minus f. This integral has to be equal to 0 for any a and b. Any a and b that you choose. So the a and b in this picture were chosen arbitrarily. We're imagining that this is a very long tube, so you could just choose a and b here. You could choose any interval a and b that you wanted. So the idea is that if you pick any interval at all, you're going to end up with an integral that gives you 0. So the only way that can happen is that if the integrand itself was originally 0. So this integrand must be 0. That's the only way that you can have the integral from a to b being 0 for any a and b. So since this is true for any a and b, it must be true that the integrand is 0. So that means that u sub t plus phi sub x must be equal to f. And this is our fundamental conservation law. Here I just wrote a reminder, f is the source term and phi is the flux term. It's standard, as I mentioned earlier in our first video, to suppress the argument xt, and so in that case we just write our fundamental conservation law in this way: u sub t plus phi sub x equals f. It is possible that phi or f depends on u, and in these cases the models may be nonlinear, and these types of problems will be more difficult to solve. Both u and phi are unknowns, but f is some given function. So in order to solve for u, we need another equation, because we still have an unknown here. So in order to solve for u, we need another equation. This is often called a constitutive relation. These constitutive relations usually come from some physical assumptions made about the model. Let's look at an example. Let's look at something called the advection equation. A model where the flux is proportional to the density is called an advection model. So proportional just means that phi is equal to c times u, where c is some constant. In this case, the fundamental law becomes u sub t plus c times u sub x equals f. This term right here, this is our flux term. So this is phi sub x, the derivative of our flux. But we're assuming that phi is equal to cu, so the partial derivative with respect to x of phi is c times the partial derivative of u with respect to x. So that's what our fundamental law becomes under this assumption, that the flux is proportional to the density. So in the absence of a source, we have u sub t plus cux, the partial derivative of u with respect to t, plus c times the partial derivative of u with respect to x is equal to 0. So when we say in the absence of source, we just mean that f is equal to 0. So if there is no source term, or no sinc term, then we have that the partial derivative of u with respect to t plus c times the partial derivative of u with respect to x is 0. A solution to this equation is given here. U at x comma t is equal to capital F evaluated at x minus ct for any differentiable function f. So it's easy to see just by direct computation that this is true. So if you imagine that u is equal to this function capital F evaluated at x minus ct, we can just compute the partial derivatives. The partial derivative of u with respect to t using the chain rule is f prime at x minus ct times the derivative of what's inside, which is minus c. So you have that term. Notice the minus c in front. If you compute the derivative of u with respect to x, again you have to use the partial derivative, or not the, excuse me, again if you're computing the partial derivative of u with respect to x, again you have to use the chain rule. But this time you end up with f prime times the derivative of the inside is just going to be 1. So you just have f prime at x minus ct. So if you look at u sub t plus c times u sub x, you end up with 0. What's quite remarkable about this is that we made no assumption on capital F other than the fact that it was a differentiable function. So anytime you have this advection equation, you can find a solution, you can find infinitely many solutions. Give me any differentiable function, and I can construct a solution to the equation. We call uxt equals capital F at x minus ct the general solution to the advection equation. If you want to find a particular value for f, then you need some sort of initial condition. When I say particular value, I mean if you want to find a particular function, capital F. If you want to determine which capital F works for a certain problem, then you need some sort of initial condition. Solutions of the type that you see here, this type, are called right-traveling waves. The name comes from the fact that for any fixed c and any fixed t, then the graph y equals f at x minus ct is the graph of y equals f at x shifted to the right by ct units. That's why it's a right-traveling wave, because it's shifted to the right. Now, right-traveling, because c is constant but t is not. C is some positive number, and t represents time. So as t increases, this value c times t becomes a larger number. So you're shifting to the right by a larger amount. And indeed, for every unit time, so if you increase time by 1 unit, then you're shifting your graph to the right by c units more. So after 1 second, you shift by c units, and then after 2 seconds, you shift by c more units to get 2c units. So as time increases, your graph starts shifting to the right more and more and more. So that's why it's called a right-traveling wave, because as time passes, you start with a graph and it shifts to the right. It just starts moving to the right. So that's why it's called a right-traveling wave. Now, as I mentioned already, in order to determine the actual value of f, we need some initial condition. Let's look at an example. Here we have an initial value problem. U sub t plus 2 times u sub x is equal to 0. So here our constant c is equal to 2. And we also have an initial condition here. So at time t equals 0, we have that the density is given by this exponential e to the 3x. Now this is just some example that I randomly made up. So the general solution is going to be u at xt is equal to capital F evaluated at x minus 2t, because you can see the c is appearing right there. But we need to figure out what f is, and that's what the initial condition is for. We know that u at x comma t is equal to what we see here. I'm just writing the same thing down for no particular reason. But that's the general solution, but the initial condition is when t is equal to 0. So x comma 0. So when t is equal to 0, this just becomes capital F at x. So u at x0 is f at x. But we know what that is. That's given to us. That's e to the 3x. So we have that capital F of x is equal to e to the 3x. The solution, u at xt, is equal to capital F evaluated x minus 2t. But now we know what capital F is. Capital F at x is e to the 3x. So you just replace this x with x minus 2t. That goes in there, and there you have your answer. So that's the solution to this initial value problem. There's actually a general advection equation which has this form: u sub t plus c u sub x plus au equals f at xt. So we have some source term here, but we also have added this a times u term. To solve this, we can use a change of coordinates. So we introduce two coordinates, xc, that's equal to x minus ct, and tau, which is just equal to t. And we define some new function which we're going to call capital U. So that's a capital letter. Capital U at xc tau is equal to little u at xc plus c tau, comma tau. So this xc plus c tau, that's our x. So if you look at this equation, we have that xc equals x minus ct. So if you solve for x, you get that x is equal to xc plus ct. Let me just fix that, like so. And of course, this is just tau. Tau is just t. So capital U is the same as little u, it's just in different coordinates. So you can actually solve for little u in terms of capital U easily enough, and so that you get little u at xt is equal to capital U at x minus ct, because that's our new variable, and t is just tau, like so. The importance of this is that we can now compute the partial derivatives of little u in terms of the partial derivatives of capital U, and we've done that here. So the partial derivative of u with respect to t, partial derivative of lowercase u with respect to t, is the partial derivative of capital U with respect to its first variable times the derivative of that first variable with respect to t, which gives us a minus c here. But there's another variable we have to consider, which is the tau. So we have to add in the derivative of u, of capital U with respect to tau, times the derivative of that second variable with respect to t, which is just going to give us 1. This right here, this is the derivative of tau with respect to t. But tau is equal to t, so that's just 1. So that's where that 1 comes from. And this right here, that's the derivative of c with respect to t. That's where the minus c comes from. So you see that little u sub t is equal to minus c capital U sub c plus capital U sub tau. That's the first partial derivative. That's this one right here. Actually, that's in our example. What I meant is that's this one right here. U sub t is that. So now the next thing we want to compute is this u sub x, and we do that right here. So u sub x is the derivative of capital U with respect to its first variable times, and this 1 right here, this is dxc dx, and that's 1. Then we have plus the partial derivative of capital U with respect to its second variable times the derivative of that second variable with respect to x. But the second variable is just tau is equal to t, so that's just going to be 0. So that's where that 0 comes from. So you simplify this and you get that u sub x, lowercase u sub x, is equal to uppercase u sub c. So if we take this u sub t equals to all of these terms and plug that right into here, you end up with these two terms right there. So this is u sub t, and then this u sub x is right there. Okay. So what does that give us? Well, here's our differential equation. So we have u sub t, which is, as we said, right there. And then we have c u sub x, that's right here because we have that c right there. That c, this c right here, is the same as that c right there. And that u sub t that's all of this. And let's just change the color a little bit. And so that u sub x, that's here, and that's here. So there's still a couple of extra terms in our original differential equation that you see right here. There's an au, but we know what u is. little u at xt is capital U at xc tau rather. So this AU, again, let's find some other color here. Let's just pick this one. So this AU is just a capital U because we've changed the coordinates. And so finally we have this F, but again we're changing the coordinates. So it's F at x comma t, but x is c plus ct. So this right here, that's x, and of course this is t. So this is some function in our new coordinate system. Now in the book they call this capital F, but we already had a capital F earlier, so I'm just going to call it capital G. So this is capital G. This is a new function. It's actually just equal to little f, but it's just in our new coordinate system. So our differential equation is what you see here. Now what's important about this is that I have ODE written here. That's because there's only one derivative with respect to tau. There's no derivative with respect to x, or rather xc in this case, because our other variable is xc. Now it's certainly true that there are these other variables in there, but you're not computing a derivative with respect to those other variables, so that means we can solve this partial differential equation using ordinary differential equation techniques. And that's what we're going to do next. Let's look at this example. Let's look at an example here. So suppose that f is equal to minus lambda mu. So this lambda is a constant here. So if f is equal to minus lambda u, then we get what's called the advection decay equation that you see here. The idea being that if your model doesn't depend on spatial location, so there's no dependency on x, then that term goes away. And then you just have the derivative of u with respect to t is equal to minus lambda u. And that is the model for decay. So this is called the advection decay equation because it involves this decay-like term. Okay, so we want to solve an initial value problem related to this advection decay equation. So we have the advection decay equation here, and we're going to insist on some initial condition. Now this is just an arbitrary initial condition that I made up. U at x comma 0 is equal to sine of x, just to give us a problem to work with. So let's solve this initial value problem. So what is the solution going to look like? Well, we start with our advection decay equation here. Notice I've just added this lambda mu to both sides so that we have a 0 on the right. So now it looks like, if I can scroll back, it looks like our general advection equation here, where c is equal to c and a is equal to lambda. So a is equal to lambda. And there's only a 0 over here. So what are we going to do with this? Well, we're going to do the same thing. We're going to change our coordinates. So we let c equal to x minus ct and tau equal t. And so that gives us the same relations between u and our capital U that we define, just as we did before. And so we end up with this transformed version of the equation that you see here, right? So that's going to be u sub tau plus a times u. Now in this case, a is equal to lambda. So that's why our equation is u sub tau plus lambda u is equal to 0. Now what about our initial condition? What is our initial condition? So we know that u at c comma tau is equal to little u at c comma c tau comma tau. So in particular for our initial condition, we have that t is equal to 0, so tau is also equal to 0. So you just plug that into here. So let me just rewrite that. So we have u c 0 is equal to little u, so this is capital U here. That's capital U. Let me just make that look like it's a little bigger. So capital U, at c0 is equal to c plus c times 0, comma 0. So that's just going to be u evaluated at c comma 0. But we know what that is. U at x comma 0 is sine of x, so we're just looking at a different variable here. So this is sine of c. So we have that capital U at x, not at x, at c comma 0 is sine of c. So now we have our initial value problem in terms of our variables c and tau. But the important thing is that, oh, this is supposed to be, I accidentally undid that. The important thing is that this differential equation can be solved by using ordinary differential equation techniques because we're just looking at one partial derivative with respect to tau. So we can do that in the standard way using separation of variables for this type of differential equation. So we divide by capital U, so it's over here, so we have 1 over capital U, du d tau equals minus lambda. You integrate both sides with respect to t. On the left, you get natural logarithm of capital U. That's supposed to be a capital U. It's a little small to be a capital U, but let's just capital U. And on the right, we're integrating minus lambda d tau. So of course that's minus lambda tau plus some constant. But that constant might depend on your other variable. Remember, there are two variables around here. We're integrating with respect to tau. So whatever you get needs to have derivative equal to minus lambda, but that's partial derivative equal to minus lambda. So the partial derivative with respect to tau of all of this, minus lambda tau plus phi psi, or xi, all of this, if we differentiate it with respect to tau, this first term will become minus lambda, and the second term will differentiate to 0. Because there are no taus there. There is a variable there. There's a xi there, but there's no tau. So when you differentiate it with respect to tau, it goes away. So that means when you're integrating minus lambda with respect to tau, you end up with this constant term, but that constant is constant with respect to tau. There might be some other variables in there, in particular xi in this case. So what do we have? We have that natural logarithm of u is equal to minus lambda tau plus this constant that it's constant with respect to tau, so it might have some x's in it. So I'm just going to call it phi, or I'm going to call it c rather, c or psi, c. For a lack of any other reason, I'm going to just call it that. So how do we get capital U? Well, we exponentiate both sides, and then we get capital U is equal to the exponential of everything on the right, which is e to the minus lambda tau plus this function of xi. So we can rewrite that in this way because we can e to the minus lambda tau times e to the psi xi. That's this term right here. And then we just call that by some new name. We call it a for whatever reason. And that's this term right here. That's this term. So now we use our initial condition. So u at c comma 0 is equal to, well, if we just plug it in here, so we've just found capital U. So if we evaluate this thing at tau equals 0, we just get that. We just get our coefficient function. But our initial condition tells us that capital U at psi comma 0 is equal to sine of psi. So this value, this function, is sine of psi. So that means capital U at psi comma tau is equal to this function a. So that's a. So again, let me just, so this thing right here is the same as that thing, is the same as this thing. Okay. Times your e to the minus lambda tau. So that's the solution to the differential equation. Now, it's in the wrong variables for our problem because we started off in terms of x and t. But we have a relationship between little u and capital U that allows us to compute little u. So little u at x comma t is equal to capital U at x minus ct comma t, And so this is arc C, and then that's our tau right there. And so now we have our solution. Now the great thing about solving differential equations is you can always check to see if you got the right answer. So that's here. We have this function u, little u, at x comma t is equal to sine x minus c t e to the minus lambda t. And of course we can just use our properties of derivatives to compute the partial derivatives. So u sub t is going to be, we use the product rule, and then u sub x is right here, because notice that this term doesn't depend on x. So when you're differentiating this with respect to x, when you're differentiating that with respect to x, that's constant with respect to x, so you just have the derivative sign as cosine. So that's where that cosine comes from. And then you have to multiply by the derivative of what's inside with respect to x, but that's just 1. So in our differential equation, we're actually multiplying u sub x by c, so that's why we've multiplied by c here. And now we want to add these two together. So our differential equation is right here. So what I want to do is I want to take u sub t, and I want to add c u sub x to it, and the objective is to get this minus lambda u as a result. So what happens if I add these two together? Notice that these two terms cancel, and you're just left with this term right here. But that is exactly minus lambda times u. That's u. So we did in fact get what we thought that we should get. Now you should check to make sure that the initial condition is satisfied as well, but it certainly is, because the initial condition just tells you that when you evaluate u at t equals 0, you get sine of x, and that's certainly the case. If you evaluate u at x comma 0, then this term just becomes 1, and then that term goes away, and you just end up with sine of x. So this function does indeed solve our initial value problem, which is what we wanted it to do.